Hello, and welcome to this lesson on sequential representations. And what we mean by sequential representations is now we're going to talk about sequential logic that has memory associated with it. And we want to talk about how to represent those, right? Instead of having truth tables and logic diagrams, we're now going to have state tables and state diagrams that show us how our sequential circuits behave and interact with each other. So first, let's talk about the difference between combinational versus sequential logic. Combinational is what we've been working with so far, and that basically just looks like this. You have some logic circuit that consists of AND gates, OR gates, NOT gates, XOR gates, all the stuff that we've been working with before. They take some input, the gates do their thing, and they produce some output. That's combinational logic. Now, sequential logic looks sort of the same, but it adds an extra component. It still has the same logic circuits with inputs and outputs, but now it has a second piece. It has what we're going to call state. You might also refer to this as memory. In addition to producing an output, the logic circuit will also now produce the next state, and it will take as an input all the way from the state memory the present state. So sequential logic has a logic circuit and a memory element, and the logic circuit takes the input and the present state and produces an output and the next state. So that's the basis of sequential logic. Let's take a look at how that works. The first thing we need is to go back and quickly revisit our flip-flops. And unless stated otherwise, we're going to always assume that we're working with positive edge triggered D flip-flops. And we go to draw these guys, they're going to look like this. They'll have some input D, which we'll call D sub something in case we use more than one. And output A, what Q was before. We're not really worried about that Q naught anymore, so we'll just kind of ignore it from our designs. And we also have that C, which won't really appear in our designs very often, but we still need to account for it. And that will take an input that from now on we will call clock. The next state gets loaded into the D input, and the A produces the present state. This can be a little bit counterintuitive. The next state is the input to the flip-flop, and the present state is the output to the flip-flop. Remember that the next state doesn't get loaded to the present state until the clock actually goes ahead and has a rising edge. So that's why the next state sits on the input and the present state lives on the output. So let's go ahead and design here a really simple sequential logic circuit. Let's do the circuit first, and then we'll talk about how to represent it. Let's say that our circuit has two inputs, X and Y, and they are XORed together. And let's say that we have a single flip-flop that has D sub A, C, and A on the output. Remember that C is connected to clock. And between this XOR gate and the flip-flop, let's go ahead and add another XOR gate. And let's tie its input from the first XOR gate, and let's bring that input around. And we'll take that and tie A to the output Z. So here's our logic circuit. X and Y are inputs, they're XORed together. They get XORed with the present state to produce the next state, and the output is itself tied to the present state. So that's the logic circuit. Now to represent this, we need two, well, we have it represented here just as a sequential logic circuit diagram, but we want to be able to draw, just like before we had truth tables, we want to have state tables, and we want to add state diagrams. Let's go from the state table first. Now a state table is going to have, on the input side of the truth table, we'll have the present state and the inputs, and on the output side we'll have the next state and the outputs. Now remember, we could have multiples of these, so underneath these columns we'll actually have the signals themselves. So under present state we just have A, and on the inputs we have X and Y, and on the next state we had D sub A, and on the output we had Z. Now we can look at this logic diagram and see that we've got some simple expressions for Z and for dA. We can see that Z is just equal to A because they're tied together, and the next state, D sub A, is just equal to the XORing of all of these. It's A, XOR X, XOR Y. So let's use that to build our, so we fill out the input side of the truth table just like always. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And then we fill out the output side kind of like normal. Let's do the Z first, that's the easiest. It's just equal to A. So that's going to be 0, 0, 0, 0, and 1, 1, 1, 1. And dA is the XOR of all of them, so that's going to be equal to 0, 1, 1, 0, 1, 0, 0, 1. That's our state table for this logic circuit. As you can see, it's basically the same as a regular truth table. And in fact, once we get it down, it behaves the same as a regular truth table. We just add additional inputs and outputs for our previous state and our next state. And we take the time to differentiate between inputs and outputs and previous state and next state. Remember, state are sort of inputs and outputs that live inside the circuit. We never see them from the outside. So that's state tables. Let's go ahead and talk state diagrams. Now, before we draw the state diagram for this state table, let's go and talk about the mechanics of a state diagram. And the way it's going to work is we draw circles for our different states. So this might be state 1, then we might have a circle for state 2, and if we had, I guess, 3 bits, maybe we'll have a state 3, whatever we have, however many states we have, we'll draw a circle to represent each state. And then all we do are draw transitions from one state to the next. So we draw a transition from state 1 to state 2, and on the transition line itself, we label the inputs / the outputs. And if we ever have more than one input, let's say from state 2 to state 3, we might have more than one input that produces the same state transition and the same output. So we'd say input, comma, another input / the output. Or if we had a state transition that involved 2 different inputs and 2 different outputs, we might have this one labeled input / output, and then comma, input / output again. So this is the structure of what our state diagram looks like. Now let's take it and let's apply it to this state table. So let's draw it down here at the bottom. Now, since we only have one flip-flop, we have one bit of state information, so that means that we're going to have two states. So we'll have state A equals 0 and a state A equals 1. Just like that. Now, we just look at our state table and see what we've got. Let's look first here at places where state A is equal to 0. Now we notice that 0, 0 gives us a next state 0 and an output 0. And 1, 1 on the inputs also gives us next state 0 and output 0. So what we'll do is we'll actually draw the state transition as going from state 0 back to state 0. And we see that inputs 0, 0 and comma 1, 1 produce output 0. And then for these middle two, 0 and 1 on the inputs gives us a next state 1 and an output 0. And a 1, 0 on the inputs gets us a next state 1 and an output of 0. So that's going to be a transition from state 1 to state 0. And that will be inputs 0, 1, comma 1, 0 produces output 0. Now let's look at state 1. And in state 1, if we have 0, 0 and 1, 1, we see that we get next state 1 and output 1, as well as, and on 1, 1, we get next state 1 and output 1. So just like before, we can draw a state transition line that starts at A equals 1 and goes back to A equals 1, and we can label it 0, 0, comma 1, 1, slash 1. And 0, 1 and 1, 0, when the present state is equal 1, gets us a next state 0 and an output 1. So we can go ahead and label that fellow 0, 1, 1, 0. And we can label that state transition line 0, 1, comma 1, 0, slash 1. And so there we have it. There's our state diagram for this sequential logic circuit. And that's really all we wanted to focus on in this lesson, right? Introduce you to what a state table is and how it looks, and a state diagram and how it looks, and also how we use flip-flops inside of our logic circuits. If you have any questions about how that works, just let me know. And if not, I'll see you guys in the next lesson. Thank you.